with a bit of extra little twist due to the additional way that we include in the structure of the data and the analysis that we do now. I restate the model. I express basically the main hypothesis, which is in the head of Bang and Olufsen when they produce this experiment, is, first of all, at least in the outset, I put the hypothesis that my 3 TV sets have no difference on their average sharpness. That's the null. I have as an alternative that at least one of my TV sets would be different than some of the others. Some difference appears somewhere. That's the alternative. It's a rather vague statement in the outset, yeah, but nevertheless, that's where we start. That's the null hypothesis. We'd like to be able to test by these data and make a decision, are the TV sets different on sharpness or not, right? The mean sharpness that we are aiming at is the true sharpness for this TV set, as it would be if we had the one and only true measurement of sharpness, not being person scoring it, but if we imagined, it doesn't exist, but if we imagined that it did, by some physical or image analysis, engineering type procedures, maybe we could set up an instrumental physical measurement that would give the one and only clear sharpness measurement as it is perceived by real people out there, because it's actually real people that are going to perceive sharpness of TVs. It's not a machine. It's real people that perceive sharpness. If we had that measurement, it's the mean of that measurement we're aiming at, right? We are trying to estimate it. The way we test it is, as we've seen last time, is by comparing, we call it also MS treatment divided by MSE. The sums of squares relative to the so-called degrees of freedom, that is the right way of averaging these sums of squares to give reasonable measures of what they're supposed to give us. Here is the fact that we need some theory that the probability people is telling us. We need to think about when I measure the difference between treatments, that is TV sets, in this kind of natural way. I mean, if even without knowing anything, that at least could be one of the options any one of us could come up with, I would say. Shouldn't I maybe study how different are the TV sets on average from each other? That's the SSTR. And probably I need to think about what is the natural variability within TV sets as a sort of noise measure. I need sort of to have a signal-to-noise ratio to have a feeling of, should I really claim those TV sets to be different or not? The F here is a signal-to-noise statistic of some kind, because in the denominator, I include the MSE, the average variability for the person as it comes out of this model estimation. So it's the average residual variability for the persons. And it turns out that if we ask the probability guy, could you please tell me, where should I make the distinction now? How large should this F be? Because it's clear when the products, when the TV sets become more and more different, this F statistic becomes larger and larger, right? Because it measures, it's a variability of means in the numerator. So that I can understand. But how large should it be to be beyond chance, right? Well, here's the probability guys. They tell us, hey, if you go compute such a group difference in this way, if you do that repeatedly in situations where the TV sets are truly equal, right, under the null, if I assume the null is true, if I assume that I compute such F statistics in a situation with no differences, I can tell you what will happen with this thing. I can tell you it will behave like an F distribution with k minus 1 and k minus 1 times L minus 1. K and L, that's the number of groups and the number of observations within groups, right? So for the TV sets, it's 2 and 7, right? 3 minus 1 and 8 minus 1. So it's 2 and 14 are the degrees of freedom to be used. That is what could happen by chance if nothing is going on. Okay, so that is my criterion to use. This is how I distinguish chance signals or random signals from real signals that tells me something, that there is a difference. I need to go check this F distribution, and if I get a signal which goes way beyond what could happen reasonably likely in this F distribution, I will claim they're different. I would say it's significant. I get, right? So I'm just repeating once again. We've done it many times now. Classical hypothesis test thinking. We can also do it, although usually when we perform experiments, this is of secondary importance, but it's kind of symmetric, actually, in the blocks and the treatments. So we could, and for the panel leader at Bang & Olufsen, sometimes it's nice to know, are my persons really different? Are my blocks different? I could ask that question also and get the answer similarly, right? We just need the right F distribution. So we would go MS block divided by MSE. We just do the same thing twice. And then we collect, let's just, you'll get your break, but let's just finish this part. Just wanted to show you one version of the F. It can look in various ways. This is how it looked. And one version of my computed F, right? So it's an F ops in relation to this null hypothesis F. And it seems like in this case it looks pretty big, right? It seems like there is a signal. Maybe I need to find the p-value to make the right decision. What is the chance to go beyond my F? My observed F, that's the p-value. We could do it both for treatments and blocks. Basically, I'm just showing you, and then I think that should be the final one before the break, because I've shown you that already, that if I do it in R, like this, I can apply the ANOVA function to make sure I get the output of the linear model presented in the ANOVA table, classic way of presenting it. Actually, I'm having a new paper coming up where I try to convince people maybe it's this classical wave we've used for 50, 100 years for historical reasons is probably for the same historical reasons not the optimal way to actually present the result, but that's just one of those historical things. That's what was done in the outset, so we do it still. And all softwares present results like that. Any kind of software you would go for ANOVA, it will present the result like this to you in the outset. It tells us degrees of freedom, source of variation, sums of squares as I have defined them to you, and those mean squares where we divide the sums of squares by the corresponding so-called degrees of freedom. Treatment -1, block -1, and then those two numbers multiplied by each other. And in a way we don't, you can also see ANOVA, our ANOVA sort of doesn't even bother talking about this one. We don't really need that. I mean, when we had, it's the other three that we need. So you don't see the total thing in the R because it's just, yeah, anyway. And then the two test statistics that I've shared with you are found to us automatically here, right? This F, for instance, treatment F 74.40 is just the mean square for treatment divided by mean square for residual. That's the two numbers divided by each other. It's not more complicated than that. Then the two p-values are found. They are found using those two different F distributions, one with 2.6, the other with 3.6, right? It goes looking for the right p-value, and it tells us in this case, treatments are different, blocks are different. Treatments with a very high degree of evidence, blocks with a lower degree of evidence, but still according to our classical 5% level, yes, they're different, right? Let's meet again in 15 minutes. Enjoy the break.